In this final video, we're going to wrap up some other concepts involving acids and bases. So taking everything that we learned in the previous lecture about analyzing structure to determine what is going to be a stronger acid, what is going to be a weaker acid, let's use that and apply it to predict the position of equilibrium. So here we have a reaction, and we have only two species that could function as acids potentially, or they could be a proton donor. So we have a hydrogen here that could be donated, and we have a hydrogen here that could be donated. So those are going to be our two acids. Notice the molecules are very similar, except for this one has an oxygen carbon double bond, and this one has a sulfur carbon double bond. So this one would be one of our acids, and then its conjugate base would be when it becomes deprotonated. This would be a base. We do not have a proton that can be removed. And its conjugate acid pair would be the acid on the other side. So in order to predict the direction of the favored equilibrium and draw the arrow longer in the favored direction, we have to be able to figure out which acid is going to be stronger and which acid is going to be weaker. We could do the same analysis with bases, but we've been primarily looking at structural differences for figuring out acid strength. So if we were to deprotonate each of our acids, we would have this for one of our structures, 2 lone pairs of electrons on the nitrogen and a negative charge. And then for our other one, we would have a very similar structure, nitrogen with 2 lone pairs of electrons, a negative charge, but we have a double bond to a sulfur. So remember your acronym ARIO. In this case, our negative charge is on nitrogen for both of them. So we can't use the atom when we start analyzing the differences between them. But in terms of resonance, both of these molecules, when deprotonated, have resonance. We have a lone pair that is allylic to a double bond, so that lone pair can be pushed in between carbon and nitrogen, and then the pi electrons would go up to the oxygen in this case. Here we would have a lone pair pushed in between nitrogen and carbon, and then the lone pair of electrons would go up to sulfur. So if we draw our resonance structure for both of these, we're going to have a double bond here, single bond here, 3 lone pairs of electrons, negative formal charge on our oxygen now. Nitrogen is left with 1 lone pair, and so it has 0 formal charge. Our resonance structure for our other potential acid, we have nitrogen double bond here, single bond, sulfur with 3 lone pairs. Therefore, it has a negative 1 formal charge. So you can see in the resonance structure a little bit better that now what we're really comparing is the stability of these two resonance structures. Is it going to be more stable when it has a resonance structure where an oxygen can bear a negative charge? Or is it going to be more stable when we have a resonance structure that has sulfur bearing a negative charge? And remember, sulfur is larger. It's right below oxygen in group 6A, and so the bigger size of it allows the electrons to spread out even more. And so that makes our acid that has that carbon-sulfur double bond our stronger acid, because its resonance structure is more stable. And so that means that our one with the carbon-oxygen double bond is going to be our weaker acid. So once we've identified the acids and we've compared their strength, recall from general chemistry that the reaction is going to be favored in the direction pointing towards the weaker acid-base pair. So if that's our weaker acid, by default, the one next to it is also the weaker base. And the other one would be the stronger base, without even going through the analysis of figuring that out. So our arrow is going to be longer pointed towards our weaker acid-base pair, or it's going to be longer pointed to the left. That means that we're actually going to have more reactants present at this equilibrium position, and we're going to have less products present. We'll have a little bit of everything, but it's primarily going to favor the left-hand side. And so we can also look up what the pKa values are for our two acids that we did the structural analysis on. The pKa for our left-hand acid is 15, and the pKa for our right-hand acid is 13. So the values correspond to what we figured out with our structural qualitative analysis. Lower pKa equals stronger acid. When we were doing reactions in general chemistry, the majority of our reactions were carried out in aqueous solutions, meaning the solvent was water. Water is not always a good solvent when running organic reactions, and learning to choose a solvent and understanding how a solvent interacts with the reaction is a very important skill. We're just going to touch on this a little bit right here, but later in the semester, we'll spend a chapter really diving in and understanding a lot more in depth about solvent selection. So when you pick a solvent, you want the solvent to be able to facilitate the reactions, so your collisions of your reactants, but you do not want it to participate in the reaction itself. The solvent should just be a medium, usually a liquid, to facilitate the reaction. But if for some reason you pick an incorrect solvent and then it participates in the reaction is not going to go forward as you predict by your mechanism. So water, we learned, is amphoteric, and that meant it can function as either an acid or a base. And so it has what we call a leveling effect on strong acids and strong bases. And what this means is that acids that are stronger than the hydronium ion, which is the conjugate acid of water, cannot be used in water because they will react with water itself. And on the flip side, bases that are stronger than the conjugate base of water, which is the hydroxide ion, can also not be used in water because they will react with water and produce a separate reaction here. So that's what this leveling effect is. And so it's important before you select a solvent for a reaction that you know pKa values. So you're taking this into account. So let's say that we're doing a reaction and we want sulfuric acid to react with one of our organic molecules. Sulfuric acid is H2SO4. If we were to choose water as our solvent to react with sulfuric acid, which has a pKa of -9, what's going to happen is the sulfuric acid will function, as it sounds, as an acid. The water's amphoteric. It will function as a base. The water is going to deprotonate the sulfuric acid, so the two lone pairs of electrons on the water will come over and grab that proton from the acid. The electrons in this covalent bond will stay with the oxygen, and so we'll form the conjugate base of sulfuric acid. The conjugate base is hydrogen sulfate, HSO4-, and this is a very stable conjugate base, which is what makes sulfuric acid such a strong acid. It has a pKa of -9. That's a very, very strong acid. Now, that's one of your acid-base pairs. The other one is going to be water and its conjugate acid, the hydronium ion. Now, notice the hydronium ion only has a pKa of -1.7. Still a decently strong acid when we're considering organic reactions, but not strong when compared with something like sulfuric acid. So sulfuric acid is essentially going to be 10 to the 7th, which is 10 million times stronger than something like the hydronium ion, because their differences in their pKa units is approximately 7 values there. So something like sulfuric acid, if you wanted it for an organic reaction, would not be good to use a solvent of water for that reaction. There will be no sulfuric acid left over to react with your organic molecule or another reagent, because all of it will be present basically as its conjugate base, the hydrogen sulfate ion and the hydronium ion. So this equilibrium will really, really favor the right-hand side of our equilibrium. It'll favor the products in this case. We have our weaker acid and our weaker base. Next, we'll look at how a base that is stronger than hydroxide cannot be used in water due to that leveling effect. So the amide ion, which amide ion is NH2 minus, it's actually an amine. When you're looking at the functional group, it's not an amide, but that is the name of this nonetheless, even though that's a little bit confusing. That's going to function as a base, and if it is in water as a solvent, the water can function as an acid. So one of the lone pairs of electrons on the nitrogen will attack the proton on the acid, and the electrons in this covalent bond will stay with the oxygen. Water will form its conjugate base, which is hydroxide ion. Oxygen has a -1 formal charge in the hydroxide ion, and our amide became protonated, our amide ion, and when it became protonated, it formed its conjugate acid. And its conjugate acid, you can see, is NH3, which is ammonia. So in this case, our amide is a stronger base than our hydroxide ion is. We mostly spent our time looking at acids and determining the strength of acids based on their structure. You can do the same thing for bases, but it's a little bit of a different analysis you would have to do. So I tend to just stick with analyzing acids and then using my knowledge that there's an inverse relationship between acid and base strength to answer questions about base strength. But this one's pretty simple, so we can look at that. Here we have one of our bases, and we have a negative charge on the oxygen. In our other base, we have a negative charge on the nitrogen. Oxygen is better able to stabilize that negative charge due to it being more electronegative. So this base right here is more stable. If it's more stable, that actually means that it's a weaker base. So if it's stable, it's happy, just like the hydrogen sorry, that got cut out. Just like hydrogen sulfate was from sulfuric acid, that was a really stable conjugate base. And so sulfuric acid was really strong. Well, hydroxide is stable due to that negative charge being on the oxygen. And so if it's happy and it's stable, that makes it a weak base. And so for the amide ion, when comparing that to the hydroxide ion, this is less stable due to we have a negative charge on nitrogen, which is less electronegative than oxygen, and less stable means more reactive, and that means stronger base. And remember, it's all relative. We're just comparing these two bases to one another. If you didn't want to analyze the bases, you could use our knowledge of structure to analyze the two acids, and then you know that once you figure out what side the stronger acid is on and what side you figure out the weaker acid is on, then that would tell you also what side the stronger base is on and the weaker base is on, because they're always together on the same side. So if we looked at our two acids then and we deprotonated them, we would have the conjugate base of ammonia is that amide ion, and the conjugate base of water is the hydroxide ion. So here we went to the two conjugate bases of our acids. And then our next step was to look at the atom. The atom told us what one was going to be stronger. So having a negative charge on oxygen was more stable. Having a negative charge on nitrogen was less stable. And so that would tell us that water is the stronger acid and our ammonia is the weaker acid. So it's a little bit of the same analysis, but it's doing it from the perspective of the acid. And then I would also know that the stronger base is on the same side as my stronger acid. Because when you analyze bases, you're looking more for stability. And then from there, you can figure out what is stronger. Whereas acids, I tend to follow the REO rules. If you are working with a very strong base, then you need a solvent that has a very high pKa value. And there are many organic solvents that can be used. So a couple examples here are something like hexane, which is just a straight chain alkane. We have 6 carbons, so the formula would be C6H, and then we would do 2 times our N value plus 2 more, so 14 for the formula. That's your quick way to figure out the formula for any alkane. And another example, well, alkane is nonpolar. So things like hexane and pentane, when you're using those, you want a nonpolar solvent to be able to dissolve and facilitate your reaction. Versus if you need an organic solvent that is polar, something like tetrahydrofuran, which is THF. This is a 5-membered ring, but it contains a heteroatom. A heteroatom is an atom other than carbon. So in this case, it's oxygen. So THF is a really good polar organic solvent that can be used to dissolve really strong bases and not interact with the reaction like water would. Sometimes 2 molecules are so similar that we cannot even use REO to explain the differences in the pKa. An example of this is something like tert-butanol and ethanol. They are both alcohols. They both will have the negative charge on oxygen. Neither of them have resonance. Neither of them have induction. They're using the exact same orbitals as well. But notice they do have different pKa's. Tert-butanol has a pKa of 18 and ethanol has a pKa of 16. So ethanol is the stronger acid. And what impacts this is the solvent effect. So solvents can surround and solvate molecules and make them more available or less available to react. So what we're going to look at is how the solvent could impact the conjugate base of each of these potential acids and how it could stabilize that conjugate base. Because the more stable that conjugate base can be, the stronger that can function as an acid. So really strong acids always have very stable, weak conjugate bases. So it's going to be the solvation effect that impacts these 2 molecules. So if we deprotonate both of our acids, what we're left with are 2 alkoxide ions. And the names of them come from the names of the alcohol they were made from. So the first one on the left is called the tert-butoxide ion. And then the one on the right is the ethoxide ion. They're ions because we deprotonated them, so now the oxygen has a negative charge. So when we look at both of these and how their electrostatic potential maps can be viewed, where it's red, where the oxygen is, that's where you have the greatest electron density. So solvents are going to come and surround your ion there at that area of great electron density where the negative charge is localized in this case. That negative charge, you see it can't be delocalized. That's why the red is only present at one location within that molecule because there is no resonance in either of these conjugate bases. So what solvents will do is they'll come and surround that molecule, and notice how little ethoxide is. We have a CH3 group here, and we have a CH2 right here, compared with something like tert-butoxide, where we've got CH3, CH3, CH3 here. We have a carbon there with no hydrogens coming off. Tert-butoxide is what we would consider a bulky, or the other word that's used is sterically hindered ion. It's big, it's bulky, and so that makes it hard for solvent molecules to get around that tert-butoxide ion and actually solvate it at all. So in this picture, what it's trying to show you is that this one might only accept 3 solvent molecules around it, whereas our ethoxide ion could accept more solvent molecules around it because it's a smaller, less sterically hindered ion. And so because the solvents can solvate ethoxide better than they can tert-butoxide, that leads to ethanol being our stronger acid, as we saw with the pKa values. So the conjugate base gets more stabilized. And tert-butoxide, we have a tert-butyl group, is less stabilized, and so tert-butanol, when comparing the two, would be the weaker acid. This type of solvent effect that we're looking at to compare strengths of acids is weaker than the other effects that we talked about when we looked at the Areo. So we are only using this analysis because Areo doesn't give us anything to compare. There is no other differences between the two, but this effect is weaker than the other ones. As we'll see later when we talk about solvents more in depth, solvation is super important when running organic reactions. The solvents are needed to stabilize something called the transition state. You might remember transition states from general chemistry. We're definitely going to look at those more in depth in this class. Reactive intermediates. You also might remember those when we talked about reaction mechanisms. And it can also allow the products to actually form through that stabilizing process of the transition state and reactive intermediates. So with the wrong solvent, a reaction might not even go forward at all. So let's look at an example here. Why is the pKa for acetic acid 4.75 in water, while it is 23.5 for CH3CN? This is called acetonitrile. And this is a solvent that is commonly used in organic reactions. So let's look at the structure of acetic acid and acetonitrile. So acetic acid is a carboxylic acid. We have an OH group, and we have a carbonyl that's directly bonded to that OH group. And we have a CH3 group on the other end here. Acetonitrile, we have a methyl group, CH3, bonded to a carbon, which is triply bonded to a nitrogen. So we have a nitrile group in that molecule. Our pKa for acetic acid, we are told, is 4.75, and our pKa for acetonitrile is 23.5. Now notice that we're specifying that those are the pKa's in water. pKa's can actually change depending upon what solvent you're using. So that's why it's good to actually be able to do structural analysis as well, since pKa's can vary. Usually when we talk about them, we are assuming that the reaction is in water, and sometimes you can use the numbers just for a general trend and carry that over to other solvents as well. But sometimes that doesn't work either, and you actually need to know what the pKa value is for a different solvent system. So just from looking at the two pKa's, we can see that the carboxylic acid has a lower pKa, so that is obviously more acidic. And our higher pKa for our acetonitrile tells us that that one is going to be less acidic. Let's also draw the structure of water and think about what could happen with water in each of these two molecules. The major intermolecular force that water has with other water molecules and can possibly have with other molecules is hydrogen bonding. So notice that if we draw the conjugate base of our acetic acid, we're going to have a negative charge on the oxygen. And that technically does have resonance. We could draw the resonance structure for that. But what we can have with water there is we can have hydrogen bonds that form. We have on the acetic acid molecule an OH bond. And for hydrogen bond to happen, we have to have hydrogen specifically bonded to oxygen, nitrogen, or fluorine. Water also can form some hydrogen bonds as well. If we were to look at the conjugate base for something like acetonitrile, the only proton that we could remove would be one of these H3s at the end. So we're going to have H2 carbon still bonded triply to the other nitrogen, and we would have a carb anion on our carbon. We also learned that that's particularly unstable is when you have to deprotonate a carbon and have a negative charge on that. So here we have no hydrogen bonding that can occur in something like acetonitrile. So water is going to be less able to stabilize the acetonitrile molecule than it could something like acetic acid. Water is a better solvent for acetic acid because they can stabilize each other with that hydrogen bonding that can occur. All right, we are going to wrap up this chapter by reminding you what Lewis acids and bases are. So we spent most of our time talking about Bronsted-Lowry acids and bases, and usually that Bronsted-Lowry definition is just fine. sometimes you do need to expand your definition to the Lewis theory in order to figure out what is a potential Lewis acid or base to figure out why a reaction would go forward the way it would. So Lewis acids and bases, a Lewis acid is something that can accept a pair of electrons. So a Bronsted acid was a proton donor. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So we flipped from the Bronsted one, accept and donate, but now we're talking about electrons and not protons. So this opens up things to be called acids and bases that we wouldn't have normally referred to them as if we were looking for a proton only. So anything that can technically accept a pair of electrons can be a Lewis acid. Anything that has a lone pair of electrons that can donate them can be a Lewis base. And sometimes the definitions overlap one another as well. Because remember, Lewis acids and bases was the biggest theory. It was the most encompassing. So if it can be a Lewis acid base, then it also can be a Bronsted one. And it could also be an Arrhenius one as well. It doesn't work the opposite way though. So the general mechanism for a Lewis acid-base reaction is you have a base, and this is just generically writing B, and it has to have at least a lone pair of electrons on it if it's going to donate those electrons. And we would use our curvy arrow to show the donation of those electrons to the acid. The acid must possess a certain characteristic also if it's going to be able to accept a pair of electrons. Usually, the acid will have less than an octet. That would be the type that you would have seen in general chemistry for sure. So if it has less than an octet of electrons, it can accept the lone pair from the base. And then what happens is a new bond is formed between our acid and our base. This is called a coordinate covalent bond. It's just like any other covalent bond once it is formed, but the word coordinate just means that both of the electrons came from the base, rather than sometimes when covalent bonds are formed, one thing will bring one electron to the dance, another thing will bring another electron to the dance, they'll come together and form a covalent bond. Here we had both electrons that were donated by the base. And so sometimes this molecule that's formed is referred to as a Lewis acid-base complex. So this slide just shows a couple of examples of the mechanism for showing a reaction between a Lewis acid and a base. Usually it's fairly simple and you just have one curvy arrow. So looking at the above reaction between water and BF3, can we identify what is the Lewis acid and what is the Lewis base? The water is donating its electrons, and so this must be the Lewis base. The BF3 is accepting those electrons, so that must be the Lewis acid. Boron is actually one of those molecules that when it forms molecules, it can have an incomplete octet. So you might remember that sometimes you actually can have less than 8 electrons around something. So notice in BF3, boron only has 6 valence electrons around it, 2 from each of the covalent bonds. So it is something that can accept another 2 electrons around it to have a complete octet. And that's what it'll do. So these electrons will get donated to the boron. I don't have to kick anything off. I don't have to boot anything off because I'm not exceeding an octet. It has less than an octet right now. And then we form that new covalent bond between oxygen and boron. That's technically that coordinate covalent bond. And notice now there's some formal charges in your acid-base complex, or sometimes called the acid-base adduct. Adduct for meaning the 2 molecules were added together. So because we started with 2 neutral molecules, overall this molecule is neutral. But we have a separation of charges on the oxygen and the boron, but they add up to 0. Our oxygen has a +1 formal charge, 3 bonds, 1 lone pair, and our boron, which normally has 3 electrons around it, has 4 around it. When we split these, we got 1, 2, 3, 4, so it has a -1 formal charge. And that's something you'll see when you form this complex. If you started with two neutral Lewis acids and bases, like we did on the left-hand side. And just looking at another example, we'll add in the curvy arrows to show the mechanism. We have our Lewis base, which is going to be the fluoride ion. That one has to be the base because it has 8 electrons around it. It can't accept another lone pair of electrons. It can only donate them. Usually a Lewis base is going to have a lone pair or a negative charge on it. So that's something to look for. The Lewis acid is BF3. We said that that had an incomplete octet around the boron. So if we take one of our lone pairs and we show it attacking the boron, we always start where the electrons are and point to where they're going towards. We form BF4 minus. And in this case, our coordinate covalent bond that was formed would be right here between that fluoride and the boron. And once it's formed, it's just like any other BF bond. You can't tell them apart. But the combination of them two would form our acid-base complex or our acid-base adduct. That's the product.